Void safety. As before, I'm assuming that you've seen the previous installments of this video series, which means that you know two of the key components to the solution, the notion of attached types. A type is declared as either attached or detachable, and the notion of CAP for certified attachment pattern. These are some program schemes that are guaranteed to be void safe. Now we are going to see a couple more interesting caps. Actually, they're quite fundamental because they enable us to have simple tests, like for example here, a void test, without having to use an object test in simple cases. So let x be an argument or a local variable of a routine. Well, if x is not equal to void, we can apply an operation with x as target. We can even, for good measure, throw in a few instructions in between the test and the application of the operation to x, as long as these instructions, of course, do not assign to x, because they could assign some void value to x. And so this is a very useful scheme, or a very useful cap. Here's another one, which is somewhat similar but applies to loops. So in the same way, let's assume that the exit condition of a loop is x equals to void. And in the loop, we have instructions that do not assign to x, except that in this case, the last one could assign to x, because then we're okay. We could assign in the last instruction something to x, and that's something to be void, but that doesn't prevent us from doing anything useful. The only effect, of course, is that the next time around, we're not going to go through the loop because the exit condition will be satisfied. Once again, x must be a local variable or a formal argument of the routine. The reason this cap is so important is that it enables us to have the usual scheme of iterating over a data structure, in particular linked data structures such as a linked list. So here, for example, we have a linked list where the first element is accessible through first, and then every element has a value item and a reference to the next element called right. The last one is known as the last one, is marked as the last one because its right field is void. And so the way we want to iterate over this is by testing if x is void, and each time through the loop we replace x by x dot right, which falls exactly under the scheme of the previous cap, since no instruction in the loop is going to assign to x, except in this case the last one. And because of this cap, this scheme is going to work. In this particular example, this is a typical iteration. We are iterating over the loop in order to seek a certain element called sort. That is to say, every time through the loop we test whether x.item is equal to sort or not. So this is how we find out whether sort appears in the list. Result will be true if and only if that is the case. And this is completely void safe. The last cap that we're going to see involves the check instruction. The check instruction is useful particularly in such cases. So let's assume that you know that at some place in the program, after these instructions here, you know, or you think you know, that x is not void. So deep in your heart, you think that x is not void, but it's not absolutely obvious from the context, and you don't want to test for x not equal to void. Of course, here, you instead of check, you could have if x not equal to void, then something, and else. Well, else what? Well, there's no else, because you are absolutely convinced that in this case, x is always going to be not equal to void. On the other hand, you don't want to use if, because in case you made a mistake, well, it's going to do nothing in the case x is equal to void, and that's also not the right thing to do because it would be a mistake. So check has the following semantics. When we check some condition, then some action, we require the compiler to do either of two things. Either the compiler can prove that at this point the condition, in this case x not equal to void, will be true in all cases, in which case everything is fine. It's just going to execute x dot operation without any overhead on performance, because there's nothing to test. Everything has been checked at compile time, so statically by the compiler. Or the compiler is not able to prove that. Now, you may be worried about this notion of proving. Well, in fact, modern compilers, in particular the Eiffel Studio compiler, are quite smart, and there are lots of cases in which they can prove that an X is not going to be equal to void. If the compiler cannot prove that, well, it is required by the language specification to generate code which, in case the condition is not satisfied, that is to say, in this case, X is equal to void at runtime, then it generates an exception. The generated code is going to cause an exception. And so you're sure that in this case, the program will have to react, or usually will terminate in some abnormal way. And this is a guarantee that you cannot ignore an X that is actually equal to void. The last point that we have to see has to do with initialization. So we saw that for attached types, which is the default, right? When I write person, it means attached person. If I wanted a detachable person, I would write detachable person. We've seen that for attached types, initialization is a key property. This was the notion of properly set. We want to make sure that entities, variables of attached types are properly initialized. What about arrays? Let's assume that I have an array of person, which really means attached array of attached person. So this is my array. Well, the array is going to be created, for example, by a creation instruction like this, using the creation procedure, the constructor make, with, for example, bounds 1 and n. So there's no problem of attachment for the array itself. It is going to be attached. But what are the array elements? Well, person is a reference type, and by default, everything is going to be initialized to void, which is exactly the reverse that we want. So if at some point we do a of I, we try to access a of I, for example, we want to print it, to take something trivial, well, we would have a void call. This is not void safe because we have initialized all the elements of the array to a void value. So it turns out that in a case like this, a creation procedure like make is not permitted. The compiler is going to reject this. There's some alternative creation procedures that you can use in such a case, and one of them, the most useful in general, is make filled. So what is make filled? Well, it's like make. It takes as last two arguments the bounds of the array, but as first argument it takes an initial value with which we are going to fill all the elements of the array. So in this case, this means that all the elements of the array will be initialized to default person, and so this assumes that we have some value default person. Didn't write here the creation instruction to create default person, but it's a person with default fields that you can easily create, an object that you can easily define and create, and then everything is fine. So this is the conclusion of our description of void safety, the end of null pointer dereferencing. It really works in practice. In modern Eiffel, there is no null pointer dereferencing, no void call whatsoever, and we have seen the key components of the solution that you can start applying right away. There's first the type system, which defines some types as being detachable and some types as being attached. Then only entities, meaning variables of detachable types, can be void. So for those, we need to guarantee the safe use of these variables, and for those we have caps, certified attachment patterns. We've also seen that a variable, in particular an attached variable, must be properly set before use, and that the key aspect is initialization, to make sure that in particular every variable that is declared of an attached type is properly initialized. These are the components. There's nothing magical. It's a construction that has these four elements, and I hope you can start right away writing Eiffel programs that are void safe and get rid forever of null pointer dereferencing.